Welcome to this video from iLearn Engineering. I'm looking at aircraft design specifically with respect to propulsion units and even more specifically, I'm going to be talking about how you would select an appropriate propulsion unit for a given flight operating regime. Let's first of all recap Newton's first law, which is sometimes referred to as the inertia law. Basically, what this says is that if a body is either at rest or is moving at a constant speed in a straight line, has to be in a straight line, then it will continue to be doing one of those two things indefinitely until something comes along and disturbs it, or in other words, an external force is applied. So let's look at an example of Newton's first law in action. Typically, a good example is to look at the trajectory of a rocket, which is going around the orbit of planet Earth, and then at some point it enters a straight line trajectory. And at this point, as long as that rocket has been given a given initial velocity, it will continue to move in that straight line indefinitely. No external force will be needed to apply to it. You won't need any energy power from the engines. It's only when you get to a point here where you want to change your speed and then eventually change direction that you need to introduce some forces from the engines. Again, once you get to this section here, straight line, no corrections, no force needed to apply. It's going to move in a straight line indefinitely. So that's Newton's first law. Okay, so Newton's second law. So this is the one which is mathematical, and it says that the net force acting on a body is equal to the rate of change of momentum. Now, momentum is mass times velocity. So expressing this using calculus is dmv by dt. However, quite often you can make an assumption that the mass term here, is constant, and if that is the case, then you can take this mass here, and you can take it out in front and put it in front of the derivative because it's a constant, and then you've got mass times dv by dt. Okay, and dv by dt is acceleration, isn't it? So you've got mass times acceleration. So that's where the more familiar F equals ma formulation comes in. So you can only use that when it's constant mass. Lots of situations when that is the case. When you're looking at an aircraft or an engine which is burning fuel very rapidly, or a rocket even more so, then you can't really make the assumption that the mass is constant. And finally, Newton's third law, which says that if two bodies exert force on each other, then the forces are equal and opposite. So they're equal in magnitude, the size of them, but they are opposite in direction. So if you were sat there now in your chair, sitting comfortably, listening, watching to this video, then you would think that your force due to your weight, so weight is a force, that is acting down on the ground, and the ground is pushing with the same force but in the opposite direction upwards to keep the chair from falling through the floor. So this is what Newton's law is, and this other force that pushes the chair up, that's called the reaction force. So with an aircraft, for instance, you've got the force of the jet um, coming out, exiting the nozzle of the propulsion unit, and there is an equal and opposite force called the thrust, which is due to the air molecules resisting that gas velocity, and they push in the opposite direction with the same value of force, and that's the thrust force that we call upon to move the aircraft forwards. Simple as that. Okay, so now let's look at some more detail here. So the thrust equation for a gas turbine aircraft engine is given here. So T is the thrust, which is the force. So M, notice the dot there on top of the M. So the dot represents a derivative with respect to time. So that is dm by dt. That's the rate of change of mass of the gas going through the engine, or the mass flow rate through the engine. And what else we got here? We've got the Vj, so that's the velocity of the gas exiting the nozzle of the aircraft, or the jet velocity, and V naught is the aircraft speed. So the difference between the jet velocity and the aircraft speed is your net velocity, and that's multiplied by the dm by dt to give you this thrust equation. So what is interesting when we look at this is that the thrust is going to vary with respect to, well, V naught is the aircraft speed. So for different aircraft speeds, we're going to get a different value of thrust, which is interesting. So if we increase the aircraft speed to this bit's bigger, then this value of this bracket is going to reduce, and so therefore the thrust will reduce. And also with altitude, we know that as we increase altitude, that the density of the atmosphere reduces, and so the density reduces, then so does the mass flow rate. So if we now look at the effect of the thrust equation on altitude, for instance, at a very high altitude, we know that the density of the atmosphere has been reduced, which means we're going to get a smaller mass flow rate and hence less thrust. So we get less thrust as we increase our altitude. However, the opposite is the case on the ground, lower down, where the atmosphere is more dense, then we're going to get a greater mass flow rate, and therefore we will get a greater thrust, which is useful when you want to take off. One of the parameters that you might want to investigate when you are looking at propulsion is the engine efficiency, which is called the specific fuel consumption, SFC, and lowercase c is sometimes used to denote this value in equations. So it is defined as the rate of fuel burn per unit thrust. So the rate of fuel burn is going to be this bit here, kilograms per second. That's how fast you are burning your fuel per second. And then that itself, that number then is divided by the thrust. So here this is the newtons is the units of thrust. So these are the SI units of specific fuel consumption, and you can find it in engine manufacturer data and on aircraft design books and websites. However, a note of caution here, big red letters, is that quite common for the specific fuel consumption to not be quoted in SI units, which is a bit you know, a problem if you're going to want to use the numbers in the formula. But however, you often find these units here, pounds per hour per pound, for instance. So this is an interesting graph because it shows the specific fuel consumption for different types of engine, and it is plotted against Mach number. Now remember, Mach number is related to the speed of the aircraft. It's the speed of the aircraft relative to the speed of sound. So in other words, you divide it by the speed of sound. So if you have a Mach number of 1, then you are traveling at the speed of sound. And if you have a Mach number of 2, then you are traveling at twice the speed of sound. Now, for most commercial aircraft, it turns out that they travel around about the Mach number of 0.8, 80% of the speed of sound. And if we would come along here, what we're looking for is one of these curves. We want the first curve we come across, which is going to have the lowest specific fuel consumption, which is the lowest rate of fuel burn, which is therefore going to be the most economical. So, and it turns out to be what we call a high bypass ratio turbofan. More about that shortly in a few later on in this video. I'll talk about that. But if you then go to the top of this graph, you will see that the aircraft, so the engine configuration that burns the most fuel is an afterburning turbojet. Piston engines. The main disadvantage of piston engines compared with gas turbines is that they have a much lower power to weight ratio. And the power output does not increase with forward speed. And most of them use gas. If we look at a basic configuration for a gas turbine, then what we're looking for is initially we have an intake, which will take the gas in, compress it some way, in other words, increase the pressure, Send it through a combustion chamber, in other words, introduce some further energy to increase the pressure even further and the temperature even further, so the kinetic energy of the gas is being increased. And then you pass it through a turbine, which is connected to the compressor to turn that, and then through some nozzle and exhaust system to help you produce some net thrust. And a typical cutaway section of a gas turbine is given here. So here you can see the air inlet. We go through a compressor, which increases the pressure here, into a combustion chamber, through to a turbine, and that turbine is connected through a central shaft to power the compressor. The gas exits the turbine through a nozzle here, convergent nozzle, where it then exits to atmospheric pressure, and we have a thrust producing machine. Gas turbines typically will burn fuel called kerosene, and variations of the gas turbine well, the turbojet is the simplest form. Then we have what's called a turbo fan. We also have turboprops and turbo shafts. So let's have a look at a few examples. Most famous example of this would be the Concorde, which had 4 Olympus turbojet engines. And you can see them in more detail on this shot. They are blanked off at the moment. You can't actually see these yellow bits are blanked off, but you can see the straight edges here, which are typical when you've got supersonic flow regime. And the engines are encased inside here, so you can't really see. But that's where they are. And there's 4 of those on Concorde. So that's a turbojet. So it's interesting that the turbojets, they were invented by Frank Whittle in the UK in about 1928. So what happens is the intake, well, that captures the air, very efficiently delivers it to a compressor, which increases the pressure and the temperature of the gas, which then goes through a combustion chamber, which adds fuel to the air, burns it, increases the temperature and engine levels even further. The turbine extracts some of that energy from the gas, which drives that central shaft, like we talked about earlier on, which is connected to the compressor. And then the nozzle accelerates. The nozzle is a convergent design, so it's designed to accelerate the gas even further. Because as we know from our earlier equation, from the thrust equation, that the velocity of the gas is important. Turbojet is very rarely used on modern. Turboprop basically means that you've attached a propeller to the front end of the engine. Turbo shaft is where we've attached, in this case, a shaft to produce useful work, which in this diagram, that shaft is attached to the blades of the helicopter. Looking at these turboprop or turbo shaft designs in a bit more detail, tend to have 2 stages. You've got a HP, which is high pressure stage, which drives the compressor here. And then we'll have a lower pressure second stage, and that drives the propeller on the turboprop. So that's this bit here, or the shaft on the turbo shaft, for instance. You also get some hot gases exiting as well. Turbofans are the most popular variant, really. They use the most popular commercial aircraft, and their design has been very successful at reducing the fuel that's needed and also reducing the noise. So turbofans, essentially, a compromise between a turbojet and a turboprop, is that the propeller is now a fan enclosed within the engine, and that produces 2 air streams. So here's the fan, which was the propeller. Now it's encased, so it becomes a fan, and some of that air gets bypassed around the outside of the main engine, and some of it goes through the central engine as it did do before. The effect of that bypass is that it increases the available mass flow rate, and therefore it reduces the jet velocity needed for a given amount of thrust. So if you remember our thrust equation right from the beginning, it depended on either the jet velocity or the mass flow rate. So because you've got a much bigger mass flow rate, you don't need as high a jet velocity, and the whole thing just becomes a lot quieter, and it improves the efficiency as well. So they're used mainly on aircraft with a Mach number of between zero point 0.5 and zero point 0.7, zero point 0.8, something like that. They are relatively small size, enables compact aircraft designs as well. So this graph is looking at the efficiency or the propulsive efficiency on which is shown on the axis here on the left as a percentage against Mach number. Now, as we said earlier on, various reasons, but essentially most commercial aircraft travel around about a Mach number of zero point 0.8. You don't want to be getting into supersonic flow because there's lots of issues and increased drag surrounding that. So this tends to be the best, one of the reasons why this is a good speed to operate at. And so we're looking for the graph, lots of different graphs here for different aircraft variations, your piston prop, a turbo prop, and how the efficiency increases with Mach number. And then here we have a turbo fan. So we're looking for the point where this 0.8 Mach number has the greatest efficiency, and it turns out to be a turbo fan design. You'll see here the worst design for efficiency is a rocket, and a turbojet is halfway between a rocket and a turbo fan in terms of efficiency. This is quite an interesting graph as well. I mean, what it has done is that it has plotted um, flight altitude in kilometers on this axis here, against Mach number again here on this axis. And these shaded areas represent groups of aircraft with various different types of engines. So turboprop aircraft tend to operate around about this Mach number. Turbofan engines tend to operate within this Mach number and this altitude. And turbojet aircraft, they tend to be for supersonic, operating at a much higher altitude. So again, you'll find that for a Mach number of around about zero point 0.8, most aircraft tend to be turbofans. And so this then prompts you to ask the question, what type of engine appears suitable for a subsonic commercial aircraft? Well, it looks to me like most of them are going to be using turbofans. Another little look at the propeller aircraft and looking at flight regimes. So the limit for a modern prop propeller, even if it's got a variable sweep with slow rotation, the limit really is around Mach number of 0.7. That's quite high. The blade pitch can be adjusted, which enables you to improve the efficiency over a range of different speeds. And the piston prop is usually for the lower Mach numbers, around about 0.4, and a turbo prop would increase your Mach number up to around about 0.7, an absolute maximum really.